Good morning, children. Today onwards, we are going to start a new lesson, and the name of the chapter is Continuity and Differentiability. In the last year, we had studied how to find limit of a function. Okay, so this year we are extending the concept of limit, and we are going to learn continuous functions. So I brought here some examples of graph. Through this, you can understand. Children, the simple definition of continuity, pictorially it means that whenever you are going or whenever you are able to draw a graph without lifting a pencil, okay, or whenever you are able to draw a curve in a graph without lifting the pencil, it is called as a continuous curve. Okay, for example, you can see this curve y equal to f of x, right? Without lifting my pen or my pencil, I can draw this continuously, right? So this is an example of a continuous function. Also, children, you can see that suppose the name of the curve is y equal to f of x, okay, and if I am fixing a point on my x-axis, say C, okay, you can see here there is a point C, and this point C can be approached from left side. Can you see the arrow mark here? This point can be reached also from your right side. That means from C plus and from C minus. That means from left side of C as well as from your right side. Alright. So what happens is, you can see in the graph, if you are trying to approach your function from, or if you are trying to approach this point from your left side, it is trying to come closer to a particular point. Suppose this point is A, children, then its image on the y-axis will be f of A. Is that clear? Similarly, when your point C is being reached from your right side, you can again see that all the values are coming closer to some particular value, right? Right from the left side or from the right side, it is trying to come closer and closer to one particular point. So this function is said to be continuous, and that point is called as limit of the function. Okay, so that's why I have written here f of C is defined and limit as x tends to C f of x exists, and you can see that whether you are approaching from your left side or your right side, your function f of x will take the value f of C. Is that clear? Now look at the second graph, children. Now here in this graph, you can see, children, y equal to f of x. If I look at pictorially, you can see a ring here. I have formed a small ring here. That means what, children? There is a break here. So whenever there is a break here in such kind of graph, the function will not be continuous. And you can see that I have to lift when I'm going to draw with this with a pen or a pencil. I have to lift my pencil or my pen, and because there is a break, and then move my hand upwards and then draw the remaining part, right? So it's a discontinuous function. Pictorially we can judge. All right. Similarly, when I look at the second definition, where it says that when you fix a point C, okay, on your x-axis, and when it is being approached from your left side or from your right side, you can see that it is trying to reach a particular point, but that particular point there is not included in the curve. So that's why you can say that this function is discontinuous. So you can see that f of C is defined, but limit as x tends to C f of x, you can see that it's trying to come closer, but that point is excluded from this. Therefore, it is discontinuous. Now just look at this. This is a step function, right? Step function is also discontinuous because if I had to move from here to here, there is a jump. Okay, so that's why this is also a discontinuous function. So here also you can see that when I fix a point C, and when it is being approached from my left side and from my right side, children, you can see that it is trying to reach two different particular values. Here you can see that it is reaching one value which is not included in the curve, and here you can see a value, right? But that is different from the one being approached from the left side. So left side limit and right side limit, if it is same, and if it is same as the value of the function at that point, then only your function will be continuous. Now just look at, this is also another example of a step function. Here also you can see that, children, there are two breaks, therefore it is discontinuous function. Also from the left or from the right you approach, it is trying to approach two values and it is not included in the curve. Okay, so here goes the definition of continuity of a point. So what does it say? Let f be a real function and C be any point in the domain. Here domain I am meaning the x-axis. Okay, you are fixing a point on the x-axis. So let f be a real function and c be any point in the domain of f. Then f is said to be continuous at c if limit as x tends to c f of x exists and limit as x tends to c f of x is same as f of c. Or in other words, it is saying that the left hand limit and the right hand limit and the value of the function at x equal to c are equal to each other, then f is continuous at x equal to c. You can see here, children, as I've shown in the graph, c minus means c is being approached from your left side, c plus means c is being approached from your right side. Then what happens? That means values greater than c is c plus, values less than c and very very close to your point c is nothing but your c minus, and that both values are same along with its value at that particular point is same, then f is said to be continuous. And it is written as if a function f is continuous at c, then limit as x tends to c, x value at c will be f of x, that is f of c. Similarly, if f is discontinuous or if it is not continuous at c, then f is discontinuous at c and c is called as the discontinuity of f. Now let us discuss some important theorems on this. Okay. So I have just written here the definition. You know that limit as x tends to c, f of x equal to f of c means your function is continuous at c. Okay, so let us see when is your function continuous on open interval ab. When will be a function continuous on open interval ab? It is obvious, children, in between all points of a and b the function should be continuous. Because it is open interval, points a and b are not included. Okay, so that's why I say a real function f is said to be continuous on an open interval if it is continuous at every point of the interval. That means between them, whatever points are there, it is continuous between every point on the interval. Now when do you say function is continuous on closed interval ab? Same definition. It should be continuous on all the points as well as at a and at b. So for that more specification is given here. A plus. Okay, that means a plus. If I go for continuity, it should be continuous on open interval ab as well as at a as well as at b. That means b minus, that means b is being approached from your left side and a is being approached from your a plus, right? Because a minus means it will go outside. So it says that limit as x tends to a plus f of x equal to f of a is same as limit as x tends to b minus f of x should be same as f of b. Why a plus? Because a plus will take you inside. Why b minus? Because b minus also will keep you inside. Okay. Now, when is a function continuous on a whole? A function is said to be continuous, right? If it is continuous at every point in the domain of f. That means everywhere it should be continuous. Now, there is some important results. Let us quickly go through it. Algebra of continuous functions. So, let f and g be two continuous functions at c and alpha be any real number. Then, f minus g is continuous at g, f plus g is continuous at g, alpha f is continuous at c, f into g is continuous at c, f by g is continuous at c, provided g of c is not equal to 0 because it is in the denominator, right? So f minus, so this we can do it by definition. So you can see f and g are continuous at c. So by definition, children, limit as x tends to c, f of x will be same as f of c, and limit as x tends to c, g of x will be same as g of c. Right? Now we want to prove f minus g. Now this same thing can be for f plus also. Okay. So if I want, I can write here f of plus minus. So this is how it will be. Limit as x tends to c, f of x plus or minus, this will be same as limit as x tends to c plus or minus of this, right? Operating at single point is same as operating individually. But this is continuous, so this will be f of x will be f of c in between plus or minus and f of g of c. Similarly here f plus minus. So operating at individual is same as operating at common point. So you can say that f plus or minus g is continuous at c. Is that clear? So similarly, children, we can prove the other results also. Okay. So again it is repeated, f and g are two continuous real functions. In the previous case we have seen that they were any function. So it was more specific. It has said here that if they are two continuous real functions also, same way, children, we can use the definition of continuity at f and continuity at g and prove the following results. Now the theorem is not so important, its proofs is not important, but the statement is very, very important. Now the next one is, let f and g be real functions such that g composite f is defined at x equal to c. If f is continuous at c and g is continuous at f of c, then g composite f is continuous at c. Okay, real functions means what? Domain and codomain both are giving you real numbers, right? So let us use the definition of what is given to you. Now f is continuous at c means what? Limit as x tends to c, f of x equal to f of c. Now g is continuous at f of c means what? When your x is approaching f of c, your g of x will become g of f of c. Now what are you supposed to prove? You are supposed to prove limit as x tends to c, g of f of x is same as g of f of c. Yes, so I have started with limit as x tends to c, g of f of x. Now by the definition of composition, this will become g of f of x. So now this will be same as, now what will happen, because f is continuous at c, what will happen? This f of x will become f of c, right? Can you see here? Because when x is becoming c, f of x will become f of c, right? So this will become f of c. So it is decomposite f of c, therefore f is continuous at c. Is that clear, children? Yes, because here it is given as x tends to f of c, g of x will become nothing but g of f of c. Okay, now the next result says that two continuous functions, its composition is also continuous. Okay, in the next class, let us see some standard examples of continuous functions.